Ionization energy. The relative ease of an element to form a cation, which is an ion with a positive charge, varies in accordance with the element's position on the periodic table. Now, in order to understand this trend, we need to investigate something that is called ionization energy. Ionization energy is simply the energy required to remove an electron from a gaseous atom that is in its ground state. For a lithium atom, the first ionization energy is the energy needed for the following process. If we draw lithium's electron configuration as 1s2, 2s1, the energy required to remove an electron from lithium's 2s orbital looks like this. If we remove this electron from lithium's outer 2s orbital, lithium will be positively charged and its electron configuration is now 1s2, or that of helium's. We show that this electron is being removed by saying plus E. The enthalpy that is associated with this process, delta H, is 520 kilojoules per mole. So in this expression that we just drew, the electron, E, is being lost by lithium. And the enthalpy needed to accomplish this process is 520 kilojoules per mole. Now, removing an electron from an atom is always an endothermic process, which means it requires an input of energy. The removal of a second electron from an atom will always require more energy. This is because when you have removed one electron, there is going to be an increase in the effective nuclear charge that is being distributed among the electrons, because there is now one less electron to distribute the effective nuclear charge among. If you'll recall, when we talked about effective nuclear charge, we said that a great way to illustrate the effective nuclear charge is to consider the amount of energy that is required to remove helium's 2 electrons. Now, experiments have shown that to remove helium's first electron requires an input of 2,373 kilojoules per mole. And of course, this is a positive number because it's an endothermic process to remove an electron from an atom. Now, to remove the remaining electron requires an input of 5,251 kilojoules per mole. Now, the reason for this increase in energy is simple. The second electron no longer experiences any shielding effect from the nuclear charge. The second electron, after the first electron has been removed, now feels the full brunt of helium's +2 charge because it's got no electrons to distribute this positive charge with. So now the entire effective nuclear charge is felt by one electron instead of two. So the general trend in ionization energies to understand is that the energy required for sequential electron removal or ionization energy increases with the number of electrons that are being removed. This phenomena is encountered with atoms that form more than one cation, such as the transition metals. The formation of a 2 plus or 3 plus charge corresponds to the loss of 2 or 3 electrons. Because when you remove an electron, the number of protons always stay the same. In a neutral atom, the number of electrons and the number of protons is the same. But if you remove 2 electrons, you've now got a plus 2 charge. If you remove 3 electrons, you've now got a 3 plus charge, and so on. The increase in the amount of energy is due to the attractive force of the nuclear charge of the cation after an electron is removed. There will always be an increase in the effective nuclear charge when you remove an electron, just simply because now you've got more protons than electrons. And the attractive force between the nucleus and the electrons will be greater. So the general relationship between ionization energy and the position of an element on the periodic table is essentially the opposite as it was for atomic radii. Smaller atoms will have larger ionization energies, whereas larger atoms will have smaller ionization energies. The size increase in moving down a given column of the periodic table correlates with less effective nuclear charge. Remember, we said that the effective nuclear charge essentially stays the same, but the principal quantum number increases. So moving down a given column of elements, the effective nuclear charge felt by the outer shell electrons will be less. Now, the greater the distance the electrons have from the positively charged protons, the weaker the attractive force between the nucleus and the outer shell electrons will be. This weaker attraction between the outer shell electrons and the nucleus means that it will require less energy to overcome the attractive positive force. In other words, the electrons will be more easily removed. So we can remove the electrons from atoms with larger atomic radii easier. So that means a lower ionization energy. For instance, lithium has the highest ionization energy in group 1A, the alkali metals. Cesium would be the element with the lowest ionization energy. And the reason is because the lithium ion, its electrons are much closer to the nucleus than they are for cesium. And so the electron that we would remove from lithium's 2s1 orbital is much more difficult to remove than cesium's electron. And in fact, if we were to rank the metals, the alkali metals, group 1A, in terms of ionization energy, lithium would have the largest ionization energy amongst the alkali metals. Next would be sodium, followed by potassium, rubidium, and cesium. Cesium has the lowest ionization energy, and lithium has the highest ionization energy. This means it's more difficult to remove an electron from lithium than it is to remove an electron from cesium. If we were to look at the periodic table, within a given period, ionization energy tends to increase in moving from left to right on the periodic table. So if we start with period 2, because period 1 is not necessarily very representative because it consists of hydrogen and helium, but starting with period 2 and moving across from lithium to neon here, the ionization energy will increase as we move across from lithium to beryllium to boron, carbon, nitrogen, oxygen, fluorine, and then finally ending with neon. And the reason this is because the effective nuclear charge across a given period on the periodic table is increasing. Thus, a greater attractive force between the electrons and the nucleus must be overcome in order to remove an electron from the atom. Now, these trends in ionization energy would suggest that an element on the lower left-hand side of the periodic table, we'll say cesium because francium is actually a radioactive element, but an element on the far left-hand side of the periodic table would be much easier to remove an electron than from an element up on the far right-hand side of the periodic table. And in fact, elements with low ionization energies tend to be metals, so either group 1A or 2A, or any of the transition metals, or anything to the left of this staircase, actually. They tend to have very low ionization energies. Metals tend to lose electrons easily, whereas the nonmetals on the right-hand side of the periodic table tend to have high ionization energies, meaning it's more difficult to remove an electron from a nonmetal than it is to remove an electron from a metal. Additionally, ionization energies tend to decrease in moving down a given column of the periodic table. And we showed this already. We said that if we started with group 1A and ranked lithium to cesium, lithium would have the highest ionization energy. Next would be sodium, followed by potassium, followed by rubidium, and then lastly, cesium would have the lowest ionization energy because the effective nuclear charge tends to stay the same for a given column of the periodic table. But the distance from the atomic nucleus tends to increase. So it is easier to pull an electron from cesium than it is to pull an electron from lithium, just because the electron is closer in to the lithium nucleus than it is for the cesium nucleus. In moving across period 2 of the periodic table from left to right, you expect to see an increase in ionization energy moving from each element between lithium all the way to neon. Unfortunately, this trend is not exactly linear, meaning they don't increase evenly between each element. We actually see peaks in ionization energy for both beryllium and nitrogen in period 2. Now, why would these two elements have ionization energies that are higher than expected? Well, just like everything else on the periodic table, the answer lies within the electron configurations of these two elements. Beryllium's electron configuration is 1s2, 2s2, and its 2s subshell is completely filled. So this leads to an additional stability for beryllium, and then therefore it will require additional energy in order to remove an electron from beryllium's outer shell, this 2s shell, 2s subshell rather. Now, in nitrogen's case, nitrogen's electron configuration is 1s2, 2s2, 2p3. Nitrogen's 2p orbital is halfway filled. And this means that nitrogen's 3 electrons reside in 3 separate orbitals. If we were to draw nitrogen's 2p orbital, it would look like this. You'd have 1 electron in each orbital, all with the same parallel spin. If you'll recall, Hund's rule says that this is the most stable electron configuration an element can have if its electrons reside in 3 separate orbitals. Now, this wide separation between nitrogen's 3 electrons minimizes the electron-electron repulsion between the negatively charged electrons, and this also leads to an increase in ionization energy. So it's a little more difficult to remove an electron from nitrogen's 2p subshell because each electron resides in a different orbital. If the stability of a given atom's electron configuration is dependent on whether a given subshell is filled or half filled, let's take this into consideration by writing electron configurations for a few cations. Sodium loses an electron to form a Na plus cation. So let's examine sodium's ground state electron configuration and sodium's cation electron configuration. Sodium, in its ground state, has an atomic number Z equal to 11, so it's got 11 electrons. And its electron configuration is 1s2, 2s2, 2p6, 3s1. If sodium were to form a cation by losing its electron in its outer 3s subshell, its electron configuration would now be 1s2, 2s2, 2p6. So sodium's cation electron configuration is identical to that of neon. And neon, as we know, is a member of the noble gas family. So in a sense, we can say that sodium is attempting to lose an electron in order to have an electron configuration that is equal to that of neon. When sodium loses an electron in its 3s subshell, its 2p subshell is now completely filled with electrons, lending to its overall stability. Now let's move down column 1 of the periodic table to potassium. Now, potassium, like sodium, forms a cation K+. So let's examine potassium's ground state electron configuration and its cation electron configuration. Potassium in its ground state will have an electron configuration equal to 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. If potassium loses an electron from its 4s subshell, its electron configuration is now 1s2, 2s2, 2p6, 3s2, 3p6. Its electron configuration is now identical to that of argon, which is also a member of the noble gas family. This pattern repeats as we move down column 1 of the periodic table. The alkali metals tend to lose an electron in order to achieve an electron configuration that is identical to the noble gas element that is at the end of the previous period. It's important to understand that quantum mechanical considerations and the effective nuclear charge dictate that the electrons are always lost from the level with the highest principal quantum number, n. For main group elements, the last electron placed into its respective subshell is the first element to leave. But this isn't exactly the case, unfortunately, for transition elements. Transition elements tend to behave in a slightly different manner. That is to say that the last electron to enter its subshell is not necessarily the first electron to be removed, unfortunately. So let's take iron, for instance. We can examine the electron configuration of iron's two cations, which are Fe2 plus and Fe3 plus, and then we can compare them to their ground state electron configuration. So this is iron's ground state electron configuration: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Now, in order for iron to form Fe2+, iron must lose 2 electrons from its 4s subshell. Thus, the electron configuration for Fe2+ is equal to 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, because it lost 2 electrons from the 4s subshell. Remember that the 4s subshell is the subshell with the highest principal quantum number, n, so those will be the first electrons to leave. Now this explains why many of the transition elements tend to form a stable 2+ ion. Iron's electrons in its 3d orbital remain unaffected until after iron loses electrons from its 4s subshell first. The removal of electrons from the 4s subshell deletes the energy level 4 in its entirety in the iron atom, and this has an overall stabilizing effect on the iron cation, since it is now an entire energy level lower. So after it loses the 4s2 electrons, it is possible for iron to lose a single electron from the 3d subshell to form Fe3+. Remember that the energy level is primarily dependent on the principal quantum number, n. To conclude, the electron configuration of atoms display a periodic variation as we move up an atomic number. In this lesson, we investigated a second periodic trend for the arrangement of elements on the periodic table. Remember that periodic law states that when atoms are arranged by atomic number, their chemical and physical properties will vary periodically. In the first lesson, looking at periodic properties, we investigated atomic radii, and in this lesson, we investigated ionization energy. Both are somewhat dependent on effective nuclear charge, but for different reasons. We said that trends in ionization energy, in moving from the lower left-hand side of the periodic table to the upper right, tend to show an overall increase in ionization energy. Now, this behavior is the exact opposite for atomic radii. Moving in the same direction across the periodic table, we notice an overall radial decrease.